Good afternoon, everyone. This project has pictures, but the focus is on the dynamics and trying to get good numbers out. I want to refer to Sarah starting a master's with Julian Orion, Justin Orion in Cape Town, Alison, and Ken. I've done whale work with him, and Miguel is looking at integrating this with a service that can be offered. What I'm going to talk about is a very simple thing. It's a narrative. Early times are on the left, time propagates to the right. Obviously, big waves break further out to sea, and you'll see as the wave breaks, it then propagates to the shore. You'll notice a lot of subtle things here you don't see looking out to sea, like energy reflected out, very clearly illustrated. If you take a ruler and measure a horizontal line, that is time. You can see that's 8 seconds, you can see that's 7 seconds. If you take a vertical ruler, you're measuring height. Okay? What we want to do is analyze that for subtle transit signatures. Here, this is not so subtle, and the question becomes, how much earlier could I have picked up something like this? And of course, it depends on background and visibility and things you can measure. So you want to have a technology that can say, hey, you can trust me now, or watch out, the visibility is degrading. Murphy was alive and well when I went up there, and I filmed fishhook, no sharks. And I couldn't see anything here, but when I analyzed this token area, I saw these little signatures. And they turned out to be little stingrays right near the bottom of the water column. So when you analyze with this approach, you can pick up a lot of signatures that you do not see when you look at that video feed. No one likes a lot of words, so I've underlined a few. We're talking about a vision system, and that really means high-quality imaging with image processing. We're targeting brief events, appearance of a shark fin, it could be a surfacing event of a whale, and I want to touch on a few specific case studies. We understand the conditions which reduce the risk because it's warning you early, or is it too late? When is it useful? Early detection must be followed by rapid response, and it's got to be an informed response. So the people, the shark spotters, they know about the response. We work with them, and we want to look at the research tool angle, accumulate transit signature statistics. So let's just touch on a few things we've been doing in multiple harbours around the country. This is a kilogram. It's a time stack. Each square is 5 seconds. 2 squares, 10 seconds between waves. Each vertical square at the coastline is 1 meter. That's the sun rising. These are waves approaching the coast. It's just a different way of seeing things, and it's much more robust for a fixed high site. You can measure the time at which things happen, like ships entering harbours. We've deployed in Cape Town, Kugge, Luderitz, Durban, and what I want to touch on with one slide is just the background. The common denominator is imaging. This is a fisheye lens looking straight up. You can track, in this case, southern lights, and to work out where things are, you need a standard reference. We use stars. If you don't want the fisheye distortion, you need to have a mirror. Now I'll shoot forward to these applications. You're looking at waves. People, when you see pictures, don't believe you can really measure height and time accurately. So here, we've got a source of waves. We developed the software for the CSIR. They on-sell a service modeling 3D harbours and other structures to various players. What's interesting is for 20, 30 years they've used probes in the water. We've been targeting multiple tracking of simple, in this case, Teflon-coated buoys. Slide up and down to test how accurate. Now, here's your standard reference. That is a known distance. Here you have the buoy, its reflection, the buoy, its reflection. The red line is here, you track the motion through time. The green line is there, you track the motion through time. You keep an eye on your standard reference. Does this work? Measure period. And the nice thing is you're not sticking stuff in the water in multiple locations. And the other nice thing is your accuracy is an order of magnitude better than conventional techniques. So, quick application, which the relevance I hope will surface in a second. Here's a model vessel. What you do is you take conventional camcorders, you bring in the video feed simultaneously, and you track the motion if your starboard and port sides move up and down at the same time, then you know it's heave. If they're in opposite directions, it's roll. So what you do is you trigger on all the different motions, surge, sway, heave, and then you can work out what's happening to a vessel. Shoot forward and realize that if you sample a line in the ocean, you'll never see a shark. The shark is going to surface anywhere. This is subtle. So in this case, there is a dorsal fin somewhere there. And I just want to touch on the work that led to this. We were working with George Branch, where Kathleen was running about 16 cameras up the north coast, and we were co-supervising with Gene Harris. And then we were unwrapping the surface of these ancient amphora. You put them in a turntable, you sample them, you spin the turntable, you unwrap that surface. Then we looked at whale census work, contract with Ken through Marine Coastal Management, as well as just tracking various harbours, Cape Town, Kucha, Durban, Walvis Bay, and Lüderitz, where we interface with the radar, the vessel tracking system, which works at night, works in all weather conditions. Okay, now shoot forward to some work done. NCC sent some footage. This is Nature Conservation Corporation. Miguel shows a day, and you can see there are a couple of surfers there. What do you get? The big point is I'm not zooming in on a target. I've got a wide field of view, and I want to track something interesting. To know where it is, you've got to work out from black rock. So if that's the horizon and this is the height of my camera, there's something here. You can use your high school geometry to work out how far away things are. So you're not just taking a pretty picture, you're working out where it is. And then you get the periodicity of the wave, the height of the wave, and then lo and behold, we start seeing other things, hence this presentation. We started seeing that you can measure both on and offshore motion, and you can measure a longshore motion through time. This was a drowning event, and once again, just to make it simple, this is very simple, so please shout and ask for an explanation if something's not clear. This green line, I can't see it. It basically should be up there, and the blue line is here. So through time, if this is a rip, now a good fisherman would see a rip immediately, but the public don't always see that. So if you've got water drifting here and then washing out to sea, a reversal in the Longshore Drift and then washing out to sea, look at the signature through time. The waves are washing past. The raft of bubbles becomes their own source. You don't have to deploy kit in the water. So through time, it displaces up the coast. Here, through time, it displaces slightly down, and water's incompressible, it's got to get out. Okay, these are currents, these are strong currents. And what's lovely about this, go back to about standard 8, that's distance, this is time. That slope is distance per unit time, that's speed. You've got the speed of the current, hard numbers. Okay. And you can see things that I knew nothing about because I know nothing about coastal environment, but small waves, and then a set comes through. The longshore drift, the slope increases, it almost doubles. So suddenly the longshore drift is modulated by the mean size of the waves coming through. You can see a lot of detail, you can see turbidity. Why is this useful? Here, suddenly behind the backline, we started seeing these little signatures. And these were dorsal fins of sharks. Obviously at low vis, you require something near the surface or on the surface. Here we started receiving canned video footage. And the guy said, check this out, there's a shark here. We'd analyze it, and we see not only that, but there was a second shark that no one knew about. So through time, as you move forward, you can track the vertical position and the horizontal position. We thought, let's try counting events. Let's look at that more carefully. There's the tail fin, there's the dorsal fin. It's difficult when they're submerged to get an accurate length measurement, but if you know this distance, tail to dorsal accurately, you know the species, you can get some indication of length. Every time it flicks its tail, it glides through the water, then slows down. It flicks its tail, glides faster again. So you get the motion through time. Now what was fascinating for me is if you start doing this properly, and what's a sweet spot, I believe, is HD footage, which is 6 times the resolution. You'll suddenly see, okay, obvious things, clouds moving out to sea. Someone bumps the tripod, you see a little displacement. And then, if you look carefully, you'll see what that is, a little surfacing event. Now, people who know their game were telling us, okay, that was a shark, that's the shark coming back. These are little schools of fish just beneath the surface. And what was interesting is that you can use a polarizing filter to get height, and you can get a much better signature. So we started looking at that. Essentially, in the whale work, we'd get an event like that, and here you'd measure vertical extent, duration. Here you'd measure horizontal extent and duration. Don't worry about the red, but if you saw anything interesting, you click on it with your mouse. It then mines out the offending clip and puts a yellow cross on the piece of video that generated that signature. So forget fancy explanations. If you see something interesting, click with your mouse, you will see the offending clip. You can have an hour of video across multiple screens. You click on the interesting stuff, and then not only can you see what happened, but you can direct a camera, if it's in the near field, to zoom in on the target before that target disappears. Okay, so these are the measurements. This is a typical event. So we picked up 80 whales a day swimming north in July. And all you do is you'd see a signature, you'd click on it, or you could alarm on it, you can do both, and you can then count the events. And you'd suddenly see, hey, through time, in 4.5 minutes, this is now 8 kilometers out to sea, there was a whale or a pod of whales moving 700 meters. Suddenly, when they disappear and they come up again, they're moving more rapidly. So they were swimming more quickly when they didn't surface. Simple things like that become obvious. Moving through to this little trial here in Muizenberg, you want to highlight transit signatures, and you want to do something that, if it's boring, tedious, suddenly you look down, shark appears, look up, it's gone. This is the technology that will fill you in for 10, 20 beaches, and it'll pop up. And just to make my case, if you look carefully again, go back to that scene, there are a couple of surfers in the water. I'm not zooming in on those surfers, I'm consciously zooming out because I want to cover a swath of backline and alert people to sharks all over the show. So here, looking at those surfers, you would see the position of the surfer through time when they all catch a wave together, when they peel off that wave. You've got their history through time. This is a narrative, essentially. It's how something changes through time. Here I'm just repeating myself. And now I just want to touch on some of the problems, the reason for the research. When can you use this? Sharks don't do this. They're not on the surface. If you look at Zambezi or Raggedtooth and the water's murky, don't even think about this, but it's one of the tools in the toolbox. If you've got reflections, it's important to use a filter. And essentially we're after that sort of signature. You've got reflections, you've got stuff on the surface. This is fairly sophisticated image processing, and therefore we want to pick up a lot of data and work out what the reliabilities are. And I mean, it's quite embarrassing. I'm talking about what you call a classic loss leader. We do this, it's interesting. There doesn't seem to be much commercial viability. South Africa has had a handful of attacks and fatalities. The real thing to do is to make the road safer. But still, there is relevance from a research perspective, and there may be interest in, for instance, in Australia, where they don't want shark nets, but they might want to know when the sharks appear and warn the public in place of having shark nets. So, just to give you another example, this chap was here, he caught the wave, he caught it at the speed, and he broke out of the wave. This guy was floating, he just punched through the wave. Second guy caught the same wave, okay? And he peeled out earlier. So this is the speed, the duration of the ride. When the guy paddles, you can see each hand plop in the water. You can see detail that you can't begin to see when you just look at the actual video. So the key term is POT, pixels on target, and you can start getting information out. Then, to be practical, and finishing off, what normally happens is you need a high sight. A high sight needs security. And you need power, so you put solar panels, but that's a problem with the wind loading. You need a robust camera that can handle high winds. So what we're trying to look at to bring costs down is something more like the citizen science we were looking at earlier, where the design concept is a room with a view. You have a camera looking through a window with a view. It's kept clean by a homeowner. You've got security resolved, you've got power, and all you want is that room with a view. What can you do? You can't use conventional cameras because quality of web cameras and image compression, you need the pristine image, and you need to migrate your intelligence upstream to an embedded system that finds these signatures. That's the image processing. And once you've got them, you send the offending frame. You've got a smart camera, you send the right stuff out. And what's very important here, forget the detail, green is good, red is a problem. In this game, if you're providing an emergency service, it has to be reliable. If the linkage back to your shark spotter detection center is compromised, these are the signals going to the cameras, pan tilt zoom, this is the imagery coming back. You want to know to all stations go. If something happens at a given high site, you're able to respond remotely to keep costs down. So what we'd really like is access to cell phone towers for power and security and vantage. And then if something happens, if someone goes live and you see an event, we track that. Okay? Here, right now, if you look at the last couple of days, it's so misty that we just switch the systems off for an hour at a time. We can't see. The blue means management said it's okay to switch off. Here, although no user would ever know the difference, a packet was being resent. So we see small things that the user wouldn't notice. Here's an event without management consent. So you want to cover multiple beaches and keep the system running. So just now asking for questions. This stuff usually comes in 3 layers. You need an imaging layer. To keep costs down, it would be great to have room with a view. You want a communications layer to take this imagery and these signatures to the shark spotters. And then you want the vision systems layer, which is the software that shows you in real time what's happening. And if you look down and look back, you can see that transit signature clearly. There has been talk of going underwater. Here you're even more subject to visibility. That is expensive. So the question is really twofold. Can this be a service to bathers and shark spotters? And can it be a research tool to track stats during daylight hours about every motion in a potential highway out to sea? It could be whales, could be sharks. Any questions?